Hello everyone. So today we're going to continue on 4.3 partial derivative. So today's video is actually should be the last video. So we have now learned how to take the partial derivative of a function, and we have learned about higher order partial derivative, but I have yet to kind of explain to you what is a partial derivative. Well, yes, as the name suggests, it seems like it should be like part of a derivative. But as a matter of fact, in itself, they also have individual meaning to it. So what I want to do is simply explain to you what partial derivative for a very specific type of function that map from R2 to R1, because those are the functions that we would use most often, and try to show you how do you interpret what the partial derivative would do, and hopefully by doing so allow you to understand what higher order or what partial derivative of other function with more variable would represent. So let's start by the following. Let's say we're going to define a function f that map from R2 to R. I'm going to call this function z equal to f of xy. Okay, oops, f of xy. What does this function represent? And yes, it is the same exact question that I'm asked every single time we define a function like this. What does this function represent? It represents a two-dimensional surface, or if you just simply want to call that surface, you can, in R3. Okay? This function has two partial derivatives. And they are df over dx and df over dy. Now, if you look at the notation we use for the partial derivative, notice it's almost exactly the same as a derivative that you have learned last year. As a matter of fact, similarity doesn't stop right there. Partial derivative, in this case, give out a single scalar, just like what you learned last year. Unlike in 4.1, where our derivative give out a vector where we call tangent vector or standard tangent vector or velocity vector. This partial derivative actually give a single scalar. And therefore, it actually suggests that partial derivatives represent a ratio between the dependent variable changing over one of the independent variable changing. Therefore, in this case, df over dx is basically a ratio between the change in f over the change in x. Okay. And what is df over dy then? That would be the ratio between the change in f over the change in y. And what do we call when we take the ratio between two things that are changing? They are referred to as slope. So therefore, first concept I want you to make sure you understand is that partial derivative are nothing more than just slope. But then comes the next question, slope of what? Well, here's the simple idea, they are technically slope of tangent. Because slope by definition should have to be a slope of a line. So therefore, both of these are actually slope of the tangent. But if you recall learning from last year, BC Calculus, when you talk about slope of a tangent, it's always the slope of a tangent of a curve. But here we don't have a curve, we have a surface. So how does this two tangent slope work? Well, as a matter of fact, you already learned how they work, you just have to make the connection. If you think about the way we calculate partial derivative, what do is that we keep one variable change. We allow one variable to change while we keep all the other independent variables as constant. And if you think about it, those exact same word I actually have said to you before in 4.2. So if you don't remember, I would suggest that you pause your video, go back to 4.2 and try to look for it. Okay, because we talk about a concept in 4.2 that kind of exactly the same thing I said. I would say that we will keep one variable changing while keeping all the other independent variable as constant. So give you a moment to take a look and then come back and see if you get the right thing. Hopefully you have a chance to try to look it up, and what I'm referring to would be coordinate curve. As a matter of fact, the simple idea is that df over dx is basically the slope of the tangent of the x coordinate curve, while df over dy is basically the slope of the tangent of the y coordinate curve. So how does it work? So, well, let me see if I can draw you a picture to show you. So hopefully, I'm not very good at drawing pictures with my writing tablet. So let's see if we can do this. So here's my x, y, z space. And let's say we have this surface. So here's my surface, z equal to f of xy. Here's my surface. And I probably draw the surface over the x-axis. So that way, over the xy plane. Okay, can it be under the xy plane? Yes, it can, but it's just easier for me to draw it over the xy plane. Imagine the following. Imagine I define a point on the bottom, which is this point, x sub 0, y sub 0. Okay, this point will corresponding to a point somewhere directly on top of it. X sub 0, y sub 0, f of x sub 0, y sub 0. So remember, the general idea here is that it basically take this point and move up to where the surface is based on what the function f of x sub 0, y sub 0 would give you. Good so far? So here comes the interesting thing. What if now I define this line that go through this point, but parallel to the x-axis? This line would be called y equal to y sub 0. And if I take, so this line have a fixed y value, but the x value actually would be changing. Okay, give me 1 second. Probably not a good idea. Oh, maybe it is a good idea. Okay, there you go. Okay, yeah, just so I cross the point. And maybe I can redraw this arrow at the end. There you go. All right, and maybe that one too. Oh, crap. Okay, I'm gonna leave it then. So now if you think about it, along this blue line, x value is changing, but y is fixed as y sub 0. Therefore, this line has only one variable that's changing, which is x. And if I plug every single point along this blue line into the function f, they would do exactly the same thing as this one point would do. It would translate up to the surface, and therefore forming some kind of curve on top of the surface. That curve is called the x-coordinate curve. In order to form an x-coordinate curve, you must fix a y value and allow the x to move. So therefore I can say that this is an x-coordinate curve at y equal to y sub 0. And so what happened is this curve would only move in two directions only. Which two directions? Because the y is fixed. It can only move along the blue line, which is changing the x value, therefore it's in the x direction, and it can move up and down by moving further away from the xy plane or closer to xy plane. And that will be the z value or the function f value. So therefore, I can now define how those two things are changing and therefore give us a slope at that point. Okay? Now, think about it. If I have the slope at that point and also know this point, I can now form a tangent line on that point that will kind of go through in the direction that's parallel to the x-axis. Now imagine I go through the same exact process, but this time do this line, which is x equal to x sub 0. Therefore, the x value is fixed, the y value is not. And therefore, now we form some kind of curve. They'll go through the same exact point, but it kind of go left to right. This curve have a fixed x value, but it has the changing y value, which is the reason why we move from left to right. And as we move from left to right, it will move up and down on the z direction because it's changing the distance from this green line to this green curve based on what the function f would tell you. So this become a y coordinate curve at x equal to x sub 0. And with the partial derivative df over dy being forming the slope at this point, and with this point, I can also write a tangent line that kind of go into the y direction. And now comes the interesting part. If I have a tangent line that go in the x direction by following the x coordinate curve, and if I have a y tangent line that follow along the y coordinate curve, and since these two tangent lines intercept at this one single point, which is the point of tangency between the two tangents, what do two intersecting lines always form? It will form a tangent plane. And we now have everything that we need to form the equation of the tangent plane. So therefore, in this case, we have a function f of xy equal to z, because this object, because f represent a two-dimensional surface, the tangent plane, its tangent planes, its tangent will be a two planes, which is therefore called the tangent planes. Notice that the important part is right here. A two-dimensional surface requires two planes to form the tangent plane. Okay? Just like a curved one-dimensional quote-unquote surface will require a one-plane quote-unquote line to form the tangent. So that's what I remember I mentioned to you, that when we talk about higher dimension object, we have different kind of tangent to it. But one of the most simple rules, something worth writing down for yourself, is that tangent to a object, they must share the same dimension. So therefore, in this case, tangent to a two-dimensional surface must be a two-plane. If I want to form a tangent to a three-dimensional surface, there will have to be three planes, and so on and so forth. So now the question is, how do we form this tangent plane? Well, of course, there's a formula for that. Here's the formula. The formula for the tangent plane to f of xy at a specific point, let's say AB, is given by this formula. Oh, I'm sorry, wrong word here. The equation, that's what I want to say. The equation for the tangent plane to f of xy at AB is given by this formula. So remember what I mentioned to all of you, that you'll be learning a lot of different tangent formula? Well, here come another one, and you will learn more. So as I say, you should definitely find a place in your notebook that title all of them, and make sure you pay attention to what condition to use this tangent formula. So in here, this tangent formula is specific to a function f that met from of xy. Okay. As a matter of fact, you know what? Let me be a little more specific. Tangent plane to z equal to f of xy. Okay, so this tangent plane formula is unique to this type of function, z equal to f of xy, meaning a function f that met from R2 to R1. So what is the formula? The formula is this: z equal to f of AB plus df over dx evaluated at AB multiplied by x minus a plus df over dy evaluated at AB multiplied by y minus b. So that's the formula for the tangent plane for a surface in R3 defined by a function z equal to f of xy. And interesting thing to note is that this right here, these two things are basically slope. And if you actually disregard this entire part of df over dy of AB y minus b, then you actually kind of have a slope formula, a tangent line formula. Okay. Now, maybe it's hard to understand what this formula looks like, so maybe we'll try an example together and show you. And also, I do want to point out is that this formula gives an equation. Not in standard form, but it is an equation, so it's not a parametric representation, unlike the tangent line formula that we learned in 4.1, which that one was a parametric representation of a tangent line. All right. So, let's try an example and see. So here, a very basic example. And we're going to let f of xy equal to 1 minus x squared minus y squared. I'm going to ask you to go and find the equation. And yes, I can tell you right now, later on we're also going to learn a tangent plane formula, but it's not an equation, but a parametric representation. So that's why I keep telling you, you have to pay attention to a lot of these little things and try to find a nice place to write down all this formula and make sure you distinguish them so that way you don't get confused. Find the equation of the tangent line, of the tangent plane at, let's say, 1/2, 1/2. So in this case, basically tell me that x sub 0, y sub 0, or actually AB, actually I use AB, so I'm going to just say AB. AB would be 1/2, 1/2. So to put the formula together, I usually try to do the following. I'll try to find these three things. F of AB, df over dx evaluated at AB, and df over dy evaluated at AB. So if I find these three things, I can then just plug into my formula and then evaluate. So let's go and start with the easiest one. F of AB would basically be f of 1/2, 1/2. So therefore 1 minus 1/4 minus 1/4. So that's 1/2, so that's easy. So that's my first number. df over dx will require me to form the derivative, partial derivative of f with respect to x first, which is not that bad. df over dx actually equal to -2x. So df over dx, evaluate at 1/2, 1/2 will just become -1. Because -2 times 1/2. df over dy would actually equal to -2y. So df over dy evaluate at 1/2, 1/2 would equal to -1 also. So now putting these three things together, I'm now ready to form my tangent plane. It will be z equal to f of AB, which is 1/2 plus -1 multiplied by x minus 1/2 plus -1 multiplied by y minus 1/2. Oops. So that's just a matter of cleaning this up. So I'm going to clean this up. So z equal to 1/2 minus x plus 1/2 minus y plus 1/2. Now what I want is to have this in what we call standard form. So what I'm going to do is move the x and the y over and keep these three -1/2, this three 1/2 together, and therefore form this equation. That would be the tangent plane formula. As a matter of fact, that would be how I would like you to write out your tangent plane equation, is to put it into standard form. Even though this equation, this formula that's given to you is not in standard form, I do want, once you plug in everything, you do put your answer into standard form. Alright? Let's see if we can do another example. Okay? So we can try, let's try this one. Let's say f of xy is equal to x times y squared plus 1. And we'll try to find the equation of the tangent plane at 0, 2. So in this case, same thing, just basically go through the motions. AB will be 0, 2. We're going to have to find f of AB, which is f of 0, 2. So if I plug in 0, 2, look to me that I will get 0. I'm going to do df over dx, which is equal to y squared plus 1. Because y squared plus a constant, differentiation of x is 1. And so if I evaluate df over dx at 0, 2, I will get 5. df over dy would actually equal to 2xy. Because it would be y squared, the derivative of y squared plus 1, the derivative is 2y, and then multiplied by x. And df over dy evaluated as 0, 2 will equal to just 0, because you have x then. So now I'm ready to put in my formula. So z equal to f of AB, which is 0, plus 5 times x minus 0, because that's a, and then plus 0 times y minus 2. So that go away, and x minus 0 is x, so therefore, seems to me, my equation is z equal to 5x, or 5x minus z equal to 0. That form my tangent plane. Alright. Maybe I put one more problems on the screen. And you guys can definitely try that one out. And then I'll also put the then we can probably go over the answer in class, or someone in class can share his or her answers so that everyone can check the answers. Okay? And that will be it for today's video. So let's say I'm going to let f of xy equal to 1 minus 2x squared plus y to the third. Find the equation of the tangent plane at 1, -1. Okay. I'll leave that problem for you to try out, and then once you finish trying out, you can maybe I just write out the answer for you so you can check your answer. So if you don't want to see the answer yet, pause the video so you can finish up the problem, and then once you finish the problem, then you can see the answers. So if I'm not mistaken, the answer is this. But of course, I could have the wrong answer, so check my answer, make sure it's right. That is it for today, and that's also the end of 4.3. All right, I'll talk to you guys later. Bye bye.